Martin Rees, first question.
Jim Peebles emphasized that we take seriously the extrapolation back to a second or a millisecond, because the laws that are relevant there are laws that we can test in the lab, etc. Do you see any hope that the laws that pertain back in the ultra-early universe that you've been discussing will have consequences which can be tested at everyday scales and in the lab? Because only if we can do that will we really have confidence in what they predict about the inside of black holes and the very early universe.
So I think the best opportunities for any observations are in more detailed descriptions of observations of the cosmic microwave background, particularly in terms of the gravitational spectrum. But I must also say, but I'm not an expert in this, that understand the full cosmological evolution and structure formation, not only from the CMB, but other measurements, adds to it. I think inflation theory is a wonderful idea, but it's incredibly flexible at this moment. So in some sense, you can get almost anything out by, it assumes a certain set of fields and a particular kind of potential, and you can always fine-tune that potential to get the result out. So I think we all agree we need a fundamental basic theory to calculate what's happening instead of just a model building. So I think that one of the perhaps hopes is, by constructing a more fundamental theory of gravity, we'll actually produce a particular kind of inflation and a particular kind of effect that we then can measure. But I think in some sense, this is all, in some sense we have to be lucky. I think both in terms of the size of the effects and the bleak scenario that Jim was just sketching, that both in terms of this early phase of the universe and dark matter, etc. There's easy to think of scenarios where these effects are undetectable, but I think I also should say, it's quite striking. If you just take a very broad point of view of what physical experiments are pointing to, or what is the interesting energy scale. Particle physics would say there's certainly three things which come to mind. The unification scale, where the various forces seem to come together. The second scale is related to the very light masses of neutrinos. And the third scale is where the Higgs particle and the vacuum structure actually kind of starts to decay. Roughly all three at that same scale. And that is also the scale that kind of inflation suggests, which is also very close to the scale of quantum gravity. So this could all be accident. But I think in some sense these hints of nature are very rare. They come at large expense. They're massive observations and experiments that have been built. But I think it definitely gives, theorists motivation to look for the solution of all these questions at one point.
Yes. Maybe the physics of 10 to the 16 GeV, which is that energy, if that has consequences at low energies, like predicting the masses of the particles or why there were three kinds of neutrinos, etc., then we would gain confidence in that theory.
Exactly.
And then we would believe what it implies about inflation or the very early universe.
Yes. So definitely all these questions are intimately connected, and I think that's again what I find is so extremely exciting. That, like to say, we look with our largest telescopes and our largest microscopes, so we're basically looking for the same answers.
Yes.
So I'm not sure exactly how to ask this question. So I hope you'll reinterpret it and and tell me what question I should have asked and then answer it. So now you began by telling us about the tension between GR and quantum mechanics, and then pointing out a few places where quantum mechanics and GR intersect, and talking about strings, which have been kind of disappointing. Let's admit it. And in the end, we don't have a real theory that unifies quantum mechanics and gravity, yet we often are talking about quantum mechanics and gravity. And from Professor Hawking, we had a description about how quantum fluctuations would lead to the kind of large-scale structures we see in the universe. And so what I'm wondering is, in the absence of a real theory that, that unifies gravity and quantum mechanics, what are we justified in doing in using quantum mechanical arguments when talking about general relativity?
So I think you have to distinguish two effects here, which is one is the behavior of quantum mechanical systems. So one point is the behavior of quantum mechanical systems, like quantum field theories, in curved space-time. So, and in some sense that you don't, like the black holes is a good example. These could be massive black holes, literally galactic size, and so the quantum gravity effects would be very small, but the quantum fluctuations of matter would be very important. And that's, that's the realm where Hawking radiation, some of these fluctuations in early cosmology come from. The second point is really go to these ultimate energies where both gravity starts fluctuating and the fluctuations of matter are important. So in that sense, there are various regimes where we are a little bit more confident than others. Is that answering your question?
Well, sort of. I guess what I'm wondering is, how justified is that confidence?
It's a good point, and in fact, it's not without debate, because typically the argument would be, if you have, say, a black hole the size of the sun, it would have an event horizon of several miles, and so in some sense it's not a microscopic object. On the other hand, if you take something which happens close to the horizon, and you look at it from a long distance, there's kind of an infinite redshift. So if you see something which looks like ordinary physics, and you trace it back, it actually was an extremely high energy event close to the horizon. So in some sense, it's also like a magnifying glass. In fact, some of the debates that are currently being held is exactly to which extent can we do this in a kind of semi-classical regime. And perhaps we cannot, and perhaps, in some sense, quantum gravity effects are already happening at the horizon or very close to the horizon of a black hole. So I would say even there, I think it's not without debate, which all points out to this point that we severely lacking a general theory of quantum gravity, although I must say, and that's for instance why the work of Maldacena and many others has been so influential, that at least on paper we have toy models where there is a working theory, and so in a very limited context you can do some of the thought experiments that you would like to do, but in the real life case.
Okay, I also would like to ask you a question. Among the many black holes in the universe, there is one at the center of our galaxy, which is observable today at a few distance of the horizon radius, and probably tomorrow very close to the horizon radius. Would you think of observational tests done in this high gravity field which could bring some light on the question of quantum gravity you were raising?
Well, I think that's probably very unlikely. I think what we probably will see, which is extremely exciting, that we will fully measure the warping of space-time as predicted with Einstein's theory. But I must say, if you think about the role of a black hole, it's often said, it's in some sense the equivalent, I feel, of the atom 100 years ago. It's something produced out of known laws of physics. It has kind of a paradox built in. You observe that nature somehow dealt with that paradox. And one elegant way to put this paradox is that, in some sense, black holes are both the most complex objects and the simplest objects that we know in nature. Simplest in the sense they're literally a hole. There's nothing there. It's the simplest possible solution of Einstein equations. There's nothing there to measure even, except the structure of space and time. On the other hand, it's the most complex object because by definition, it's the most efficient way to store information. So a black hole of a certain size is like the maximal efficient storage disk, because it has the maximum amount of information that can fit into it. So in that sense, actually going into an area where we not only, of course, with the exciting development of gravitational waves, got direct detection, but we also will see kind of in the electromagnetic spectrum, actually be able to observe them, I think is absolutely crucial. Because I think, just like the cosmic singularity, and I said they are close cousins, I think they will just provide for us, at some point, the right ideas to solve this kind of mystery.